Yeah, I can. So we're very happy to have Esty Kelman from Tel Aviv University giving the next talk. It's about proof for the seminal result of KKL and also for other results by also seminal by Frigot and Talleyrand. And this is a exciting new proof technique for these very fundamental results analysis of Boolean function. And Esty is a PhD student, and we already heard about their exciting work on the Fourier entropy conjecture, and now we hear about their other exciting work. So I'm very looking forward to the future to see more works by Esty. Okay, so.
Okay, thank you. So thank you, Avishai, and thank you, Avishai and Prasad, for organizing this workshop. I'm really excited to be here and to feel that I'm in San Francisco. I put a picture that Muli contributed to this presentation. So, okay, I will talk about the work or that Avishai presented. This talk about KKL type results, and I will explain why I call all of them KKL type. And we use alternate proof for the KKL and the other theorems. I will show this in this talk only the proof for the KKL, but same techniques works also for the Friedrich-Strunter theorem and the Talleyrand inequality. And this is joint work with Subhash Khot, Guy Kindler, Dor Minter, and Muli Safwa. So let's start. I'm going to turn off my camera, and if I will need, we'll open it back. Feel free to ask any question. I guess that I will miss the questions in the Q&A, so I'm sure you're about on it. Okay, thank you. Okay, so I will give a very brief and short introduction for the Boolean function analysis in general. It might be a little boring for the experts here, but it will be short and you will get to know with my notations. I actually tried to find the notations of analysis of Boolean functions, but it's turned out that there is no notation. Every paper uses another notations, and maybe Ryan O'Donnell books is what the notations of the analysis of Boolean functions, and I try to stick to his notations, but okay. So the Boolean functions are functions on the Boolean hypercube. They might be Boolean valued or just values from R. We define the inner product as we see every function as a vector on 2 to the n values. And then the inner product is fairly trivial. And in these functions, we have the parity functions that are the set of interesting functions that actually consist the basis, the orthonormal basis of this vector space of Boolean functions. And then we can represent every function as a linear combination of those parity functions. This is well known as Fourier transform. And then we have the f hat is the Fourier coefficient for every character, which is a parity function, which is, and the way to calculate the Fourier coefficient is the inner product between f and the appropriate parity function. So I'm sorry. I will talk a little about influences. So we have the derivative functions for every direction I. The i's derivative the partial derivative is just how much the function change in the I direction for every x and for every input. And we can see that for Boolean valued functions, the derivative functions are also very similar to Boolean. They have only 3 values, -1 and 1, that say what is the direction the function go, and 0 if it doesn't change in this input and direction. The Fourier representation is very easy to calculate from the definition. And we can see that this is the part of f that actually live on characters that contains I for every i's direction. So the inferences are defined to be the L2 squared norm of the derivative function, and for Boolean valued functions, it's actually the probability of the ith bit to change the value of the function for every for random input. For another functions which are not Boolean valued, it's measure how much expectedly the value change, the value of the function change on the direction I. We can see it if we think about a Boolean valued function and we look at all the edges in direction I. This is a fraction of those edges that change the value. And we have the Parseval, which is the Parseval equality that we use not only here but a lot, which says that the L2 squared norm of the values is the same as the sum norm of the coefficients. And then we have that the i's influence is exactly the weight of f that lies on characters contain I, like all the characters that involve in the direction I. And another interesting object that we'll look at is the total influence, which measure, it's defined to be the summation of all the influences, and actually what it measures is the probability of an edge to be influential in all over the cube. It's also known as the average sensitivity. So up to normalization, this is a probability of an edge to be sensitive. And again, the Fourier presentation of the total influence is very easy to calculate it from the definitions. And it's, if we think about the Fourier representation of f, the Fourier coefficients squared as a probability space, then we get that this is also the expected character size, which we also can call as the expected degree, which we'll talk about the differences between the maximal degree and the expected degree, when we want to use each of them. So this was just a brief introduction, and now we'll continue with another introduction, and we'll talk about the KKL type theorems. So I have here the definitions of the individual influence and the total influence, at least for Boolean functions, these Boolean valued functions, which are ones that we are concerned with. And let's see, so what is the KKL theorem? The classic version of it says that for any Boolean functions, let's think about balanced functions, then exist some variable with high influence, are large, at least log n over n. We know that the trivial one is that for at least Boolean functions, the total influence is at least 1, and then there exists at least one individual influence, which is at least 1 over n. So the KKL says actually that there is an individual influence with non-trivial influence, which is a factor log n. And we can see what's behind this KKL theorem. There is another version which is dimension free, and it implies this classic KKL immediately. It's sometimes easier to work with it. Sometimes it's easier to just we just need to prove it in order to get a KKL. So what it say that there is always exists some large individual influence. How large? It's larger than 2 to minus the total influence, or the total influence normalized, how I wrote it here. What's mean that either the total influence is large, let's see how it implies the KKL, the classic KKL. So either the total influence is large, which means that we have a trivially large individual influence, at least 1. And otherwise, if the total influence is small, then this bound gives us individual influence, which is large. And actually, it's much larger than the log n over n, which we need. So, okay, so this is a KKL theorem, and now we'll talk a little bit about Friedgut. We'll see how it generalizes the KKL, and we'll continue from there. So just I put here a reminder, what is a KKL? We say that there is some individual influence which is larger than 2 to minus the total influence. And the Friedgut-Junta theorem, what it says is that for every Boolean function, f is close to small junta. How small? To the influence. So I don't care about constants. I just omit them from everywhere. So how it generalizes the KKL. So let's see about the proof idea of the Friedgut-Junta theorem. The first step is to choose all the individual influences that are large. How large? We know from the KKL theorem that there exists at least one variable with significant individual influence. So let's take all of them, all of the large influences. And what the proof actually shows is that the part of f that lies on characters that involved only with variables with I influence takes almost all the weight of the function, and therefore this can be the junta. And there are not a lot of them because they are large. So what showed that all the weight outside J of every character that involved on non-influential variable is negligible, which means that we just can drop all the characters with any non-influential variable, and still the function is very similar to what we begin with. So it's pretty clear how to generalize the KKL. Just for formalization, we'll say it. So the KKL shows that there is at least one significant influence, and the Friedgut-Junta say that most of the weight is actually concentrated on the significant influences. So what about Talleyrand's inequality? This is generalization of the KKL, very immediate. So it says that every Boolean function, the Talleyrand sum, which we have in the right-hand side, is bounded from below by the variance. And if we think about balanced function, this is actually some constant. So Ronen talked about it last week and said that each summand here is somehow represents the variance in direction I. I just take it as it is. I don't really understand what's mean, but this is some meaning of this. But you see that it somehow says something about the probability of the influences if we choose a variable according to its influence. So it's involved. It's not exactly the entropy, but somehow we have here the log 1 over the influence. So somehow we can connect it to the entropy of the influences distribution. But let's see how it's generalized the KKL. So just take the maximal influence in the log term, and we actually get exactly the KKL. We can rearrange the inequality and we get KKL. So we have these three theorems. Actually, the Talleyrand Friedwurz and the KKL is inside them. And all of them are not, they're not new. So let's talk a little bit from when they came. So the original proof for KKL is from the 88, the Friedwurz from 10 years later, and Talleyrand's inequality is in between. And what's common for all of these proofs, the key technique that they used in the original proofs of all these theorems is the well-known hypercontractive inequality. So what's the idea of the hypercontractive inequality? So the basic of this, using the noise operator, which smooths the functions and somehow reduce norms. In the proofs of those theorems and a lot of other proofs in analysis of Boolean functions, we use some corollary of the hypercontractive, which involves with the maximal degree of the function. What happened is that when you take a Boolean function and apply noise operator on it, it takes the rate from large levels down, and somehow you get a function which is close to small degree in some cases, but it's not of the maximal degree. So the way to use it is to cut the function at some degree, and then we get a function of maximal degree, which we know exactly what is it. But what we lose in these functions is that now they are not Boolean. If we have started with Boolean function and we apply noise operator and then cut it, they're not Boolean, and sometimes they are even not bounded. And these cases are, it's hardly to use, to get back the results from the hypercontractivity, to say something about the difference between norms.
So just to clarify, when you apply the noise, it is bounded, but when you truncate, it's not necessarily bounded?
Yeah. Exactly. So anyway, they use the exact meaning of the hypercontractivity is a little bit mystery, and we've wondered whether there is life beyond the hypercontractive inequality. And certainly there have been efforts to prove the KKL theorems and strengthening theorems of it without using the hypercontractivity. The reason is not only because it's a mystery, and also because it's hard. The hypercontractivity have its limitation using the maximal degree, and it's hard to get new results using these techniques. So what we've done is to just prove the KKL theorem and the other theorems without using the hypercontractivity. And this is actually the work. We show alternate proof for existing results that doesn't use this hypercontractivity. And we hope that our techniques let us prove new statements. So what is our technique? So our result is actually a unified approach for all of these three theorems. We use the same techniques for all these three theorems. So in order to understand what actually is the KKL say, it says something about the structure of the function. If all the influences are small, then the total influence is large. So in order to understand the structure of function, we want to make it simpler. So simpler functions are functions of lower degree, for example, less variables. So the way to take functions from large degree to small degree, so one way is to use the noise operator. Another way is to use random restriction. In random restriction, we actually look at subcube, and that way we get maybe simpler function, which we can analyze better. So our goal is, I will tell you it now, is to get to functions with I want to say of degree 1, and we'll be very happy if we have functions of degree 1 because we know exactly what are they. They're only dictatorships, and this is the easiest way to analyze something. So we'll not get exactly there, but this is our mission. So for that, we will use random restrictions, trying to get there, and we'll see how we do it. The other tool we need is when we get to the functions of degree 1, we need to analyze them somehow. So if they were exactly 1, we are done. But they are not, so we need exactly other tools. So we'll use the log Sobolev inequality. So what is the log Sobolev inequality? I brought here some version of it. This is not the version we use, but this is the version which is the most similar to the hypercontractivity. So it actually looks the same. The only difference here are that the hypercontractivity uses the maximal degree and the log Sobolev use the expected degree. Okay, the expected of size S is the expected degree. This is a total influence up to normalization, which we get if we think about the Fourier coefficients as the distribution and take every character with probability fs squared, then this expectation is actually the expected degree. So why it's so important to use the log Sobolev and not the hypercontractivity? So as we said about the hypercontractivity, it uses the maximal degree, which sometimes we need to cut the function in order to use this hypercontractivity. And when we take a combination of functions or do some induction of a function, we can take, for example, a function and partition the characters to disjoint sets in some way and analyze each part of them as a separate function. And then we combine them together, back together. Then in the hypercontractivity, the maximal degree might be the maximum of the maximal degrees of the combinations of the function involving the combination. But in log Sobolev, if we want to combine back functions, it's much easier. If we, for example, take a function and separate its characters to disjoint sets, the expected character size will be the average of the expectations. Therefore, the log Sobolev gives us a stronger tool in this sense that we can actually, we have the additivity of the parameter, and also we don't have to cut functions. If we have a function which is somehow Boolean or bounded, we know that it's still bounded. We don't lose this. Yeah.
So it seems that the log Sobolev inequality is stronger than the hypercontractivity, right? Because the expected size of the set is always smaller than the degree.
Yes, in some sense it's stronger. In some sense it's even equal.
Okay.
And I'll tell you why it's even equal. I guess that you can just prove the log Sobolev using the hypercontractivity. But when you use it, yes, it's stronger. Just see that you have the norms there. So log Sobolev, as far as I know, works exactly for these 2-1 norms. When the hypercontractivity more flexible with the norms. But when we talk about Boolean functions, then it's not really matter because all the norms, all the moments are equal. So it's just up to some constant here. Okay, so what we'll do in this talk, we just talked, we waved hands.
Just to clarify whether I'm understanding the inequality right. If f was Boolean, this would be like the left-hand side would be the influence, and then the right-hand side would be 0, right?
If it's -1,1, yes, it will be 0. But if it's 0,1, you get there. You actually get the edge isoperimetric inequality, the standard one.
Okay.
You see that, yeah? Okay.
Okay.
Oh.
And
so,
yeah.
Okay.
There was another question in the chat. They were asking, what is the size of the set S? Like, what does this notation mean?
Okay, so S is a subset of N. I will go back to the slide of the, just 1 minute. Here. So we have the parity functions. For every S, we have the parity function, which is exactly the variables that their indices are in the set S. And then we have for every character which involved with this S, we have the Fourier coefficient of this S, and S is the size of this subset. There are subsets of N. Okay, you can see here in the basis, we have S is subset of N, and for each subset. And when we talk about the total influence, you can see that the Fourier representation of the total influence is the summation of over all the characters, the size of S times the Fourier coefficient squared. So if we think about the Fourier coefficient squared as probability, then we get here exactly the expected character size, which also we call the expected degree, because for each size of characters, this is some level, some degree of the characters. Okay. And so
every Boolean function defines a probability distribution over sets, where the probability of something a set is Fourier coefficient squared, and then you take the expectation with respect to this.
Okay, thank you for clarifying.
I have a question. So in the definition of hypercontractivity, you have the denominator f in the norm with 3/2, and in the log Sobolev you have f of norm 1. Is this like an important difference, or can you say something about that?
So the hypercontractivity is much more flexible with it. You can take every number between 1 and 2. The log Sobolev is somehow, as far as I know, is used only the norm 1. Again, for Boolean functions, it's not really matter because all the moments are equal, and then we get there only different constant because it's in the log. You can think about it as if you take the hypercontractivity instead of 3/2, you take 2 minus epsilon norm. Then you can think about it as epsilon coverage to 1. And maybe you get somehow the log Sobolev and the limitation. I'm not sure about the details, but there is something like this. There is.
Okay, thanks.
Okay. So in this talk, we will prove the KKL theorem and give all the techniques along the way. We'll develop our tools. I'll cheat, I'll not say a little bit, I'll cheat a lot in the first hour. I hope we'll have enough time to fix all of this cheating. But if not, it's also okay, because the proof idea will be in the first hour. What I mean to be the first hour, I'm not sure if it will be, actually, if it will fit the time. Okay, so just for state of the art, what are the other proofs that are hypercontractivity free? So there is a work of Dvir Felik and Alex Samorodinsky from 2007. They proved the KKL theorem and the Friedgut-Hunter theorem. They also used the log Sobolev inequality and not the hypercontractivity. The difference is they had different approach than what we do, and their proof doesn't seem to be extendable to the Talleyrand's inequality. Another work is by Ronan Eldan and Renan Gross, very recent. They used a very different approach, which is very, very interesting. They used stochastic calculus and analysis of jump process, and Ronan talked about it last week. Anyone that missed it is welcome to see it in the website. And then our result that also parallelized to this result somehow. Okay, so just a reminder, we are going to prove the KKL theorem in the version that say that if all the influences are small, then the total influence is large. So from now on, we just assume that all the influences are small, and we'll try to prove that the total influence is large. So let's start with random restrictions. We just use it to, in order to simplify the function to get structures that are easier for us to understand, then combine all of them together in order to get our result. To get a structure on the function f. So let's start with the restriction, which is not randomized. So what is a restriction? We just choose, there is some subset of variables. Let's say f is of n variables, and some variables will be free, and some of them we will give them some fixed value. And that's how we choose a subset of the subcube to look at. So we just define J will be the alive variables from now on, the variables that are not constant. And Z will be the assignment for the other variables, which is from now, for now at least, constant. And then we get a new function from it depends on J and Z that we choose. And it takes values on the subcube -1, 1 to J. This just mean values for the variables in the set J. Say to R. What is the value of this function for any point, any assignment y1 to yk? It will take exactly the value of f in the same point. We just look at the subcube and get same values. Okay, so the restriction, we can have some formal definitions for restrictions. And what's very interesting is how the Fourier transform of the restriction looks like. We already know the Fourier transform of f, and let's derive the Fourier transform from the restricted function for any restricted function. So just a formal definition for those that doesn't like too many animations. So let's note something before we go to the Fourier transform. If f is Boolean valued, that is all the values of f, say 1, 0, 1 or -1, 1, then every restriction is also Boolean valued function. Okay, it's pretty trivial. We just look at subcubes, or it's same values. It's subset of the values that f can get. Okay, just to make it clear. Let's think about an example. So if we have, for example, the address function, which takes k plus 2 to the k inputs, where the first k is the address, they choose one of the other variables to be their dictatorship. It looks like this. We have k variables and 2 to the k, and the first k choose one dictatorship as the binary value. This is the index of the dictator. So if we choose J to be the set of 2 to the k variables, and we fix some address, it's very easy now to understand the function, the restricted function fjz. It's exactly a dictatorship. Okay, for every z, it will be the same. Okay, so let's see the Fourier representation. So for every f restricted function f, we can think about it as the function of z and y, where z is constant. So we can use the Fourier a bit delayed. Okay, we can use the Fourier expansion of f and just put there both z, the constant part, and y, which is the free variables. And because the parity functions are homomorphism, that's how it's called? Not sure. There are kifliot, how I say it?
Multiplicative.
Yes, this is okay, this is how it's called. Okay, doesn't matter. We can separate the z on the variables that are outside J and y on the variables inside J. And then we get that the part of z in the parity function is actually constant now. So it's go together with the Fourier coefficient, and we have only the part of S that inside J, that the intersection of S and J, the alive variables in S. This is actually the new character. So what we have here, it looks like a Fourier representation, but it's not exactly, because we have every, it's not exactly how we used to see it, because we have every character here might appear more than one time. Different characters S might have same intersection with J, same set of alive variables. So let's sum up all of them together. Just for every potential character, subset of the alive variables, we take together all the characters that have exactly those variables alive. And this is exactly the Fourier coefficient of the subset T. And we already have this, some representation of this Fourier coefficient, and we can see that it's actually, as a function of z, we have exactly the Fourier representation of this Fourier coefficient. So let's denote it as GTZ, just to make sure that this is a function of z and not of t or something like this. Just fix some t. We have GT of z, a function of z, and we have the Fourier representation of this function, which is actually the part of f of the characters that their alive variables are exactly the set T. So this is GT is a function that grows from the subcube of the values outside J to say R. Okay, it's not anymore a Boolean function. There's no reason for it to be a Boolean function. You can think about it as a tableau of the characters and the different restrictions, where in each place in the table we have the Fourier coefficient for the character and the appropriate z. So if we fix some z, some restriction, and look on the for the row, we have all the Fourier coefficient for the restricted functions with z. And if we look on the column, we have some subset of J, character of J, and we have the different values of it, of the Fourier coefficient of it for different restrictions. Okay, this is important, and we'll see it again later. So let's now, it will be interesting to think what happened if we randomize Z, for example, if we choose random Z. So for now, we take the random restriction. It's exactly, it's almost same as before. We have the J, fixed J, which is alive variables. And now we random each value of Z uniformly at random. Each value is -1 with probability half or 1 otherwise. We again get a function, but now this function is a random function. So we can think about it as a random variable. We can think about other interesting parameters that are randomized now. For example, we can think about some character. What is the expected value over Z of the Fourier coefficient of this character? So once we have the Fourier representation of it, it's pretty easy to see that it is exactly the empty character of the Fourier representation, which is the Fourier coefficient of T in F. So we'll go for other more interesting parameters. This is not very interesting one.
We've lost your audio.
Esty, are you still here? Maybe we should take a short break because maybe Esty has some technical difficulties. So let's get back in, say, 10 minutes. Let's take the break now. Hopefully things will